In this lecture, we discuss higher order derivatives and we focus on acceleration and concavity. So what do we mean by higher order derivatives? We know that if we are given a function f of x, then we can find the derivative of this function. It's denoted as f prime of x, or different notation, df over dx. This is called Leibniz notation. Both of them denote the first derivative of f of x, of the function f of x. Okay, and we learned how to do that, how to find the derivative using the definition of the derivative or using the rules of differentiation. Now, if we want to find the second derivative of f of the function with respect to x, then we need to find the first derivative first and then find the derivative of that. For example, if f of x equals x squared plus 3x, then f of prime, the first derivative, is 2x plus 3. And then to find the second derivative, we differentiate this function again. So we differentiate the derivative. So this is 2. If we want to find third derivative, this is 0 because the second derivative is a constant. That means the third derivative is 0, and so on. So that's what we mean by higher order derivatives: second derivative, third derivative, and above. Now, in physics and even in some economics problems, we can talk about the position, velocity, acceleration. So what do we mean by position? Position is a function that depends on t, and that determines the position of something with respect to time. For example, position of a particle with respect to time. So s of t denotes position of a particle or something or object at time t. And s prime, the derivative of this, is the velocity. Now, velocity of t is s prime, derivative of the position, and this is the velocity at time t. And if we find the second derivative of s, the second derivative of s is denoted as a of t, and that is the acceleration at time t. So that means acceleration is the first derivative of the velocity and it's the second derivative of the position. For example, if we are given the position s of t, position function t cubed minus t, and we want to find the acceleration. To find the acceleration, we first find the velocity. First derivative of this, which is the velocity, is 3t squared. And then we find the derivative of the velocity, which is the second derivative of the position function, and that's 6t. This is a of t. If we want to compute it at specific value, we just plug that value into the formula of a of t. Now, the notation for the second derivative, f double prime of x, or d squared f over dx squared. This is just a notation that denotes the second derivative of the function f of x with respect to the variable x. Okay, now let's take an example, some application of higher derivatives. For the first 15 months after the introduction of a new video game, the accumulated sales can be modeled by the function s of t equals 20e to 0.4 t units sold, where t is time in months, so after about 25 months, the total sales follow more closely the curve s of t, the curve of the function s of t equals 100,000 minus 20 e to the power 17 minus 0.4 t. Now the questions are, how far are accumulated sales accelerating after 10 months? And then we ask, how far are accumulated, how fast are they accelerated after 30 months? Now, what do these numbers mean? Okay, now we want to answer this question. We are given two functions depending on the time. So let's find, for the first part, we want to find acceleration after 10 months. So 10 months is still within the first 25 months, so we use this formula. So s of t is 20 e to 0.4 t, and then we find in order to find acceleration, want to find acceleration at time 10, a of 10, acceleration at time 10. So we find the first derivative of s, which is 20 times 0.4 e to 0.4 t, because as you may remember, the derivative of the exponential function e to the power f derivative is derivative of the power times same exponential function, and here this is derivative of the power times same exponential function. And if we simplify, we get eight e to 0.4 t. So this is s prime, or ds over dt. Now we find the second derivative. To find the acceleration, we need to find the second derivative of s. A of t is the second derivative of s with respect to t, or you may use this notation, s double prime of t. Now this is the first derivative, this is the first derivative, s prime. Now we find the derivative of this to find the second derivative, so we differentiate the derivative with respect to t. This gives us 3.2 e to 0.4 t. So this is acceleration. We want to find it after 10 months. So that means a of 10, this is equal to 3.2 e to 0.4 times 10, which is equal to 3.2 e to power 4, and using the calculator we can approximate this by 175 units per month squared. Per month squared. Why? Because it's per month per month. The first derivative gives us the velocity per month, and then the second derivative per month, so that's the velocity with respect to time. Derivative of that is the related or the rate of change of the velocity, which is month per month, and that's per month squared. Now total sale, in this case, total sale is s of 10. S of 10 is, we substitute here to the original function to find the total sale. It's 20 e to 0.4 times 10, and this gives, or can be approximated by 1.092 units. Now what does this mean? This means by the end of the 10th month, a total of 1,092 videos or video games have been sold. Okay, that's the total sale. And what does this mean? Let me use different color here. What does this mean? The first derivative. The first derivative with respect to t, evaluated at t equals 10. So let's find it here. ds over dt evaluated at t equals 10 is 8 e to 0.4 times 10, and that is 8 e to the fourth, can be approximated by 437 units per month. So the interpretation here is that the game is selling at rate of 437 units per month. Now the second derivative gave us 175. Let's interpret this: d squared s over d t squared, which is the acceleration evaluated at t equals 10. It's acceleration at time after 10 months, and this is the rate. Now this is equal to 175 units per month squared, and this represents the rate of sales. This means that the rate of sales is increasing by 175 units per month per month. That means per month squared. So more games will be sold each month than the month before. Okay. Now what happens after 30 months? Because part B asks us to see how fast are they accelerated after 30 months. So we want to find A after 30 months. So after 30 months, we can't use the first function. We can't use this function. But we need to use the second function, this function, because this deals with 25 months or more. So we use this formula for the S of t. So S of t is 100,000 minus 20 e to 17 minus 0.4 t. Now we find the first derivative, which represents the velocity. The velocity is negative 20 times what is derivative of the exponential function. Derivative of the exponential function is derivative of the power. What is times the same exponential function? What is derivative of the power? 17 is constant, so derivative is 0. Negative 0.4 t, derivative of this is negative 0.4 times same exponential function. So this gives us 8 e to 17 minus 0.4 t. Now let's evaluate this at t equals 30. So when t equals 30, this is 8 e to 17 minus 0.4 times 30. And using calculator, we find that this can be approximated as 97.032 or comma units per month. Now what is the second derivative? D squared s over dt squared. This is the acceleration at time t, and this is negative 3.2. What is derivative of the derivative? What is derivative of this? It's 8 times negative 0.4, derivative of the power, times same exponential function, and that gives us negative 3.2 e to 17 minus 0.4 t. And then we find we evaluate the acceleration at time 30. So this is d squared s over dt squared at t equals 30. You can use any one of those two notations. You don't have to write both notations here. So negative 3.2 e to 17 minus 0.4 times 30, and using calculator you find that this can be approximated by negative 475 units per month squared. Okay, now by the end of the 30 months, 97,032 video games have been sold. The game is selling at a rate of 1,187 units per month, and the rate of sales is decreasing because the second derivative here is negative. The second derivative is negative. That means the rate of sales is decreasing. The rate of sales is decreasing by 475 units per month. Now fewer games are sold each month than month before. Okay. Now let's talk about, we talked about acceleration. Now let's talk about the concavity. Concavity. What do we mean by concavity? The concavity function tells us, or the second derivative here, the second derivative of the function tells us what direction the graph of f curves or bends. So we find the second derivative. This tells us about the curve, the concavity of the function. For example, here the second derivative is greater than 0, positive. That means the curve of the function is concave up. If the second derivative of the function is less than 0, that means the graph of the function is concave down. And that's it. So by using the second derivative, we can determine concavity of the function. So if we have a graph like this, if this is the graph, a graph of function f of x. Here, as you can notice from this graph, here at this point, approximately at this point, let's call this the point A. At the point A, the function or the graph or the function starts to change its concavity. So as you can see, the concavity changes at this point, and it changes here at this point as well. It's called this point B. So those points where the function changes its concavity are called inflection points, or points of inflection. Point of inflection. And this is another point of inflection. And here the derivative, since the function is concave down here, the function is concave down here, that means the derivative, second derivative, will be less than 0. And here the function concaves up, that means the derivative here, second derivative, is greater than 0. And here the graph is start concaving down, that means the second derivative here is less than 0. Now let's take an example. If we are given f of x equals x squared plus x plus 1, and we want to find the intervals where f of x, the function, is concave up or down, and then find the points of inflection, if any existed. So in this case, we need to find the second derivative. So we first find the first derivative. So f prime of x is equal to 2x plus 1. And then we find critical point. So f prime of x, we make it equal to 0. 2x plus 1 equals 0. And that means 2x equals negative 1. And then solve it for x, we get negative 1/2. This is a critical point. Now we find the second derivative. The second derivative is 2. we don't have x here, so we can't set the second derivative equal to 0. This is impossible. So that means, so this is a critical point, but we don't need the critical point here. We need the 0 of the second derivative of the function, but here we don't have 0 of the function, but the function is always greater than 0. For all points here, the second derivative, I mean, is greater than 0 for all points here, so it's concave up all the time. So that means f is concave up on the interval -infinity to infinity. And is there any inflection points? No, because the function does not change its concavity. No points of inflection. There's no points of inflection. And here, as I mentioned, you don't need to find the critical points, because you don't want to find the intervals of increase or decrease or these things. Now let's take another example, but that example is an application. So we will talk about inflation. So the value of the US consumer price index, denoted as CPI, from September 2013 through August 2014 is shown in the below figure. So here on the x-axis, let's denote this as t time, and the y-axis denoted as I of t, the inflation depending on time. And here we have 233, 234, 235, 237, 237, 238, and 239. And on the t-axis we have 0 here, and here 232, 2, 4, 6, 8, 10. And the curve, when we graph the curve, we get a graph like this. And then start concaving down. So we are given the formula for this function. I of t is given by -0.0225 t cubed plus 0.390 t squared minus 1.20 t plus 234, where t is between 1 and 11. So here 0.0 denotes September 2013. So here, when the function I of t is increasing, the US economy is experiencing inflation. And what does that mean? Increasing, that means the first derivative, this is one of applications of the first derivative, increasing or decreasing. That means the derivative is greater than 0. The first derivative is greater than 0. And what is the inflation rate? Inflation rate is usually given by the following formula: I prime of t over I of t. So we need to find I prime of t and I of t in order to estimate inflation rate. So the first question is estimate inflation rate. So to do so, we need to apply this formula. So need to find the derivative of I. So let's find the derivative of I here. I prime is, now we need to differentiate this function I. So what is the derivative of this? Derivative of this is negative 0.225025 times 3t squared plus 0.390 times 2t minus 1.20. Now we find the inflation. Now we need to substitute t equals 4. When time t equals 4, so when t equals 4, in this case we have, we want to find it. Let's estimate inflation rate at some point. So let's estimate this at January 2014. That means t equals 4. January 2014. That means t equals 4. So in this case t equals 4, so the inflation rate is I prime of 4 over I of 4. So when we plug these values here, we find that we obtain 0.48 by substituting 4 here, and divide by I of 4. So we need to substitute 4 here, and that gives us 234, and the answer can be approximated as 0.0036. This is the inflation rate. Now for part B, we want to find if the inflation slowing or speeding up in January 2014. Now to determine this, we need to find that if the second derivative is less than 0, we need to find the second derivative. Second derivative is less than 0, then it's slowing. If the second derivative of the inflation function is greater than 0, then it's speeding up. So let's see. Let's find I double prime of t. We need to differentiate this, the first derivative, with respect to t. So derivative will give us negative 0.135 t plus 0.780, and then we plug 4 into this formula. We get negative 0.13135 times 4 plus 0.780, and using calculator we find that this is equal to 0.24, and this is positive. Since it's positive, then it's speeding up. So it is speeding up in January 2014. Okay, now another question, or we want to ask, when is inflation slowing? When is inflation slowing? And when is inflation speeding up? And when was inflation slowest? Now by slowest we mean if we have a curve that looks like this, then at this point it's the slowest. Okay, so to answer this question, slowing, that means concave down. That means the second derivative is less than 0. The graph looks like this. And speeding up, that means concave up. The graph looks like this, and that means the second derivative is greater than 0. So let's answer this question. Let's find the second derivative. We already found it from the previous part B. And then we set this equal to 0. So when we set this equal to 0, we solve for t. T is 0.780 over, we can bring this to right hand side, it becomes positive, so we have 0.780 equals 0.135 t, and then divide both sides by 0.135 to get a value of t. The value of t can be approximated as 5.8. Okay, so here we have 5.8, and this is the second derivative of I, the function I. And if we choose a value greater than 5.8, like 6, and substitute it into the second derivative, this is the second derivative. If you substitute a value greater than 5.8, like 6, substitute 6 here and use the calculator, you find that this gives you a negative value. If you substitute a value here like 1 and substitute it here into the second derivative, you get a positive value. That means here the function is concave up, and here it's concave down. So it's slowing down on the interval, this interval, from 5.8 to infinity, and it's speeding up on this interval because it's concave up, from speeding up on the interval negative infinity to 5.8, and the slowest point is this, the inflection point. So slowest point is at t equals 5.8. So here the function stopped speeding and began slowing. Okay. Now the last part of this lecture is about second derivative test. Second derivative test. Second derivative test of relative extrema. Here we suppose that f is a stationary point. I mean by stationary point the derivative is equal to 0. F has a stationary point. I should write it here. F has a stationary point, I mean x, where alpha prime of x equal to 0. Let's call this x C, the point x equals C, where the first derivative at C, evaluated at C, equals 0, and the second derivative at C exists. Then we have three cases. First, if the second derivative evaluated at C is greater than 0, then f has a relative minimum at x equals C. If the second derivative evaluated at C is less than 0, then f has a relative max at x equals C. So if the derivative is greater than 0, second derivative evaluated at C is greater than 0, then f has relative min. And if the second derivative evaluated at C is less than 0, then it has relative max. Now if the second derivative evaluated at C is equal to 0, then the test is inconclusive. So in this case, we need to use the first derivative test, I mean to find the first derivative and set the critical point here and study the sign. If it's positive negative, then it's max. If it's negative positive, then it's min. This is the first derivative test because we used the first derivative. But here, this is the second derivative test. Now let's take some examples. For example, if f of x equals x squared minus 2x, we want to determine the relative or extreme values, relative extrema. So we find the first derivative. First derivative is 2x minus 2. And then from this we find the critical point, or the stationary point. 2x, we set this equal to 0. 2x minus 2 equals 0. 2x equals 2, and then divide by 2 to get x equals 1. This is a critical point, which is a stationary point. So we found the critical point. Now we find, so this is the value of C. So this is C. Now we find the second derivative. The second derivative of this is just 2. Now we plug C here. C is 1. But we still have 2 because we don't have x here. It's greater than 0. If the second derivative evaluated at C is greater than 0, then we have, or the function has a relative minimum at that point. So f of x has a relative minimum at x equals 1. Let's take another example. If we are given f of x equals x cubed minus 3x squared plus 9x, here we find the first derivative, 3x squared minus 6x plus 9, and then set this equal to 0 to find the stationary point. 3x squared minus 6x plus 9 equals 0. We can simplify. We have something in common here. We have 3 in common. So this is x squared minus 2x plus 3 equal to 0. Now we can factor this. So we have 3 times x minus... Okay, let's change this to negative. Let's change the sign of positive 9x to negative 9x. So if this is negative, then x minus 3 times x minus x plus 1 equal to 0, because negative 3 times 1 is negative 3, negative 3 plus 1 is negative 2, the sum is the middle term. So the solution for this is x equals, we have two cases, x minus 3 equal to 0 or x plus 1 equal to 0. Solve this to get x equals 3, solve this to get x equals negative 1. We have two critical points or stationary points. Now we need to find the second derivative and plug these values into that formula. So the second derivative is derivative of the first derivative. It's 6x minus 6. Now we test these values. Second derivative of 3 is 6 times 3 minus 6, and that's 18 minus 6, which is 12, greater than 0. That means x equals 3 is relative minimum, because it's the first case, its derivative is greater than 0. Now let's plug the second value, negative 1. 6 times negative 1 minus 6, that's negative 6 minus 6 is equal to negative 12, less than 0. That means x equals negative 1 is relative max. Is the second case. Now let's take the last example in our lecture. If we are given f of x equals x to the fourth, here we find the first derivative, which is 4x cubed, and set this equal to 0. That means 4x cubed equal to 0, and x cubed equal to 0 by dividing both sides by 4, and that means x equals 0. This is stationary point. After that, we find the second derivative of the function. We find the second derivative, that means the derivative of the first derivative. It's 12x squared, and then we substitute our stationary point to get 12 times 0 squared, and that's equal to 0. But if the second derivative is equal to 0, that means our test is inconclusive. So the test is inconclusive. In this case, we use the first derivative test. The first derivative test says that you study the sign of f prime. F prime has a 0 at x equals 0. Then you try a value greater than 0. Let's choose 1. Substitute it into f prime. You get positive. Substitute value less than 0. Let's choose negative 1. Substitute it here. You get negative 4, which is negative. Decreasing, increasing. That means this is relative minimum. But we relied on the first derivative test. We didn't use the second